Hello, good morning, everyone. Today we have a well-known personality in the field of astrophysics. That's Professor Varun Bhalerao. He's an astrophysicist at IIT Bombay. He obtained his BTech degree in electrical engineering from IIT Bombay, and that is followed by a PhD from Caltech in 2012. During his thesis, he worked on New Star, the first focusing hard X-ray telescope, a Caltech JPL NASA mission. He also studied high mass X-ray binaries with optical and infrared telescopes to measure neutron star masses. As a Vaidya Rai Chaudhary Prize postdoctoral fellow at IUCA, Pune, he led the ground calibration of the cadmium zinc telluride imager on AstroSat, the Indian multi-wavelength space telescope. At IIT Bombay, his group works on the development of Growth India, that's India's first fully robotic telescope. The group leads the Indian effort in the study of elusive electromagnetic counterparts to gravitational wave sources. He is the principal investigator for the proposed Daksha mission, that's the world's most sensitive telescope for high energy transients, about which he will tell us today. Varun Bhalerao is a recipient of the Venu Bapu Gold Medal of the Astronomical Society of India. He is also a former associate of the Indian Academy of Sciences and recipient of the DSP Inspire Faculty Fellowship. He has been awarded the IIT Bombay Early Research Achiever Award in 2019, the Kriti Ramamitham Award for Creative Engineering again in 2019, and the IIT Bombay Departmental Award for Excellence in Teaching in 2023. He has published more than 100 refereed papers. So we have here Dr. Professor Varun Bhalerao today with us, and he will now talk to us about Daksha mission. Thank you, sir. Up to
Hello.
you now. You can start with your presentation.
Thank you, madam, for the warm words. And thank you to all the organizers for arranging these great sessions and inviting me here to talk about this. So, before getting to Daksha, I thought I'll start with a basic introduction to multi-messenger astrophysics. Okay, now multi-messenger astrophysics, the name sounds quite a mouthful. So what are messengers? Okay, messengers are basically different ways in which you get information about the universe, right? So you're all used to all of these, of course, but I am going to talk about slightly different messengers as compared to this. So how do we learn about the universe? Now, astrophysics in that way is a very unique physical science where instead of going and doing an experiment, I'm limited to seeing what experiments others are doing. So, for example, you are all science students. Imagine that at some point, instead of doing a chemistry lab, you are told to stand in the building next door, observe one of your seniors doing an experiment, just look at the test tube from far away and figure out what's happening in that, right? And that is what astrophysics has always been. And that means we actually have to try really, really hard to get all the information that we really need in order to understand all of these sources. And the backbone of that, of course, has always been photons, right? The first thing that you do is you look at stars. If you ask someone what astronomers do, people will start by saying they look at stars, galaxies, and everything. So photons have been our primary source of information. It started with just optical and then went into what is called multi-wavelength or multi-band astrophysics or broadband measurements, where we look at different types of light, and I'll come to that in a bit. But then in the last decade or so, we have gotten the advantage of having more sources of information. So for example, we have gravitational waves available to us, where it is not just a different kind of radiation, it is entirely different physics. It is not just light of a different wavelength, but a completely different form of information that we can get about the universe. And the last one, of course, is particles. I'm not going to go into particles a lot today, but let's talk about the first two messengers. Okay, so the first messenger that we have is photons. Now, you're all familiar with this concept, of course, that light comprises of photons of different wavelengths. If you go to shorter wavelengths from the optical, then you get X-rays and UV and gamma rays and so on. On the other hand, if you go to longer wavelengths, you get infrared, submillimeter, millimeter waves, radio. In fact, one of the issues with doing radio astronomy from the ground, for example, is FM radio, which interferes with the signals that we want. So with all of this light, each wavelength gives us a different picture about the object. And in India, we've been using a large number of telescopes to study these objects. So this is a gallery of telescopes which are currently active in India. Here's a little challenge for you. Take a screenshot of this slide and let us see later how many of these telescopes you can actually identify. These are all being used actively in India for research right now. One of them, by the way, is Asia's largest telescope currently. Of course, two can't be Asia's largest. Uh, so what do we do with photons? Okay, now any field that you are studying, you have two broad categories. First is what is it that you can actually observe? So when you see a photon, what is it that you are measuring? So the first thing you measure is the direction from which the photon came. What was the wavelength or frequency of it? You do something called timing studies, where you study at what time the photon actually reached you. And you can also measure polarization of the photon. So where the photon was, what direction it came from, the wavelength, timing, and polarization. This uh, set completes all the properties that you can measure about any photon of any type out there. And then using these observables, the next question is what are the inferences that you can make? Okay, so direction, of course, tells you where the source is located. In case you can resolve the source, you can actually make out its shape. For example, if you look at the moon, then you actually see that there are features on the moon. If you look at a galaxy, you can see maybe a nice spiral shape. The wavelength and frequency, we do spectroscopy, and that is used to infer temperature of the source, composition of the source, and many other properties. Timing actually deals with variability. So was the intensity varying with time? You may have heard of concepts like pulsars, where we detect a pulse sometimes every few milliseconds, sometimes every few seconds. And then finally, polarization often tells us information about magnetic fields and conditions on the source. So with all of these put together, this has been the backbone of astrophysics for decades, okay, or centuries rather. All of the astrophysics, all the great inferences that started off back from even before Galileo, going all the back to Kepler and everyone, was just done on the basis of photons. The new kid on the block is gravitational waves. Okay, so gravitational waves are emitted. This is a simple animation from PhD comics explaining how gravitational waves are created. So I actually have a question. On my screen, this thing is appearing to freeze a little bit. Is it a fluid animation for all of you, or are you also experiencing problems seeing this?
It's
It is the
freezing
same.
for us also.
It's freezing for you also. Okay, so I am actually going to stop sharing my screen for a bit. Let me try to fix this problem. It should not have occurred in the first place, but I'm suspecting that something in the background is slowing down my machine. So I'm just going to kill everything that was running in the background. Okay, I should leave item on and pretty much everything else can close. So now I'm going to try screen sharing again. This is a bit odd. I've been doing presentations for so long and this has never happened. So clearly today the universe wants us to slow down, I guess, for whatever reason. So how many of you, so I think you're all allowed to raise hands, although you can't unmute. But the question for all of you is how many of you have heard about gravitational waves before? Let's just see a show of hands. I see five, six. I would expect that number to be much larger. So let's keep those hands up for a little bit. And I'm going to use that to decide how much I should talk about gravitational waves. Okay, so that is only about a fifth of you. All right. So I will talk about gravitational waves. And at this point, let me try screen sharing again. All right, let's get back to this animation and let's see what happens. Nope, still going slow. Okay, one more thing now, and let's see if that works. Okay, I might have figured out what the problem was. All right, is this smoother now?
Yes, sir.
Okay, great. All right, so sorry for the interruption. The universe has hereby been rebooted and it is working fine. So this is a simple animation from PhD Comics, which shows how gravitational waves are created. So you may have heard about this analogy where if you have some heavy object that you put in space, then these lines here are a two-dimensional representation of space. Remember, space is not two-dimensional. So this analogy can only be taken so far. But when these objects are present in space, they actually distort space around them. And now if these two objects are actually orbiting each other, then as they orbit, that distortion has to move along with them. Okay, and as it moves, it causes these disturbances to propagate through space, and those propagating disturbances are what comprise gravitational waves. Okay. Now, in practice, as I said, space is not two-dimensional. So suppose you are looking at your screen right now and the gravitational wave were to come out of the screen towards you, then this is what would actually happen to the screen. Okay, so the particles that comprise the screen here, we have denoted them as rings of particles. They actually get stretched along the side and squished from the top at first, and then they get squished from the side and stretched upwards. So with the stretching and squishing that is going on, this is what the result of a gravitational wave is. Now the effect that is shown here, of course, is highly exaggerated. In practice, this is not how it goes. In practice, the effect is extremely small, and we'll talk about it in a minute. Now, this just shows you what is happening on the surface of your screen. What about the rest of it? So if I now extend this into 3D, then what you get is, okay. If you want to see more of this, again, just scan this QR code and this will take you to a software that you can load on your phone or on your laptops or whatever, which where you can load up a camera and just see what happens if a gravitational wave were to pass through you right now. Okay, so I'm not going to go into this demo here because universe already has been glitching once. I don't want to take a chance, but scan this QR code and you'll go to that demo. So to extend this now from this 2D space, what does the wave look like in 3D? So it would look something like this, that at one surface when it is squished, remember this is just following the wave equation. While it is not an electromagnetic wave, the equation again will have a kx kind of component in the exponential and a omega t kind of component. So when the part at the back is flat, the part in the front might actually be stretched up instead. This also somehow reminds me of these, by the way. I don't know what inspired what, but sandworms from Dune. Anyway, what generates gravitational waves? The most common source we have seen by far is the merger of two black holes. So what you are seeing here is a simulation of what you would see if you were standing close to two black holes as they merged. This is actually a simulation for the first event ever detected, which was detected in, so the name of the event is written down here, 150914. So the event on 14th of September 2015. And I'm going to play this animation again. You can see that the background stars appear to be distorted, and that is because of gravitational lensing. So light is actually bent by the strong gravity of the black holes, and these two black holes, as they are coming closer, as they are orbiting, they are emitting gravitational waves. So they are losing energy, which means that their orbit actually shrinks. They come closer to each other until at this point they touch and finally merge into a single black hole. Okay, so this was studied extensively using gravitational wave detectors. A lot of Indian scientists played very important roles in this discovery. But all of this, of course, is giving us only gravitational wave data. We wanted multi-messenger astronomy. And the sources that you are seeing here, represent the first bunch of sources that were detected. And what you can see is they actually follow a lot of different masses and thereby a lot of different um, time scales for merger. So on the upper right here, you are seeing the time scale. You can see that this is of course greatly slowed down. And again, just to pause here, the peak frequency at this, okay, at this point, just when these things were about to merge, they were rotating around each other faster than the spinning of, say, F1 car wheel. Okay, so extremely heavy objects, 30 times the mass of the sun, moving extremely fast at relativistic speeds. And as the masses change, the shape of this waveform that is detected in gravitational waves changes. So here, for example, you have a system with a more extreme pair of masses, and you can see that the waveform that is being plotted at the bottom now lasts much longer, and the amplitude on the other hand was much lower. So by studying the waveforms that we see here, we can infer things like rough location on the sky, the masses of the systems, the rough distance to the system, and so on. But what is of particular interest to me is systems that comprise of neutron stars plus black holes, which we study. And I'll come to that in a little bit. So how are these detections done? Here is a flypast of LIGO Livingston. This is one of the four operational gravitational wave detectors around the world right now. You can see that there are these extremely long arms, and what you're seeing at the bottom is what is called the central station. The arms are both 4 kilometers in length, and you can see end stations all the way out there. What happens inside of these arms? My slides seem to be in a slightly different order. That's awkward. We are going to get a detector exactly like this in India, by the way. So this is the photo from the actual site of LIGO India. This is a site located in central Maharashtra at a place called Aunda Nagnath near Nanded. And construction work on LIGO India has already started. So the fifth gravitational wave detector in the world is going to be in India. So, how are the waves detected? What I'm going to show here is a simplified animation of how the gravitational wave detectors work. So, this point here and this, all of this would have been in the central station that I showed. These arms would be 4 kilometers in length, and there would be mirrors in the end stations. And this basically is an interferometer that detects gravitational waves. So, we have an extremely stable and high power laser. That laser beam is incident on this beam splitter, which sends it into the two sides. The beam actually gets reflected from the two end stations, and then it comes back. It will combine here, and as you expect in a Michelson interferometer, you will get an interference pattern there. So initially what is done is that the arms are tuned to be the same length. So when the arms are tuned to be the same length, the pattern is completely destructive, and you don't sorry, not the same length. They're tuned such that the interference is completely destructive and no light comes down over here. When a gravitational wave passes through this, so if a wave were to come from top and go through this figure as you are seeing it right now, what will happen is that the length of these two arms will start changing. Now, the gravitational wave strength is measured in units of something called strain, which is the fractional change in length. And that fractional change is extremely tiny. It is about 10 raised to minus 21. So in order to measure it, you need to have extremely long arms. So your delta L divided by L is 10 raised to minus 21. Even when you put the L to be 4 kilometers, your delta L is still smaller than the diameter of a proton. Okay, so there are a lot of physics tricks that are used in order to measure an effect this small, which I'll not go into at this point. But what happens as a gravitational wave goes through this is that with the arm length changing, you switch from constructive to destructive interference here and back. And the intensity of light on the detector placed here at the bottom is what changes. And that is what is measured. And it is on the basis of that that we detect gravitational waves. Okay, so you can see here again that as you go from constructive to destructive interference, the intensity of the light that is reaching there is going to change. So moving on, um, the objects that, as I said, are of most interest to me are another kind of merger, which is the merger of a pair of neutron stars. So I know you have heard about neutron stars before. They have a surface, so they can actually emit light. And in the collision, you have a massive explosion. So you eject a lot of material out here. You launch these massive jets. If you happen to be exactly along this jet, you see something called a gamma ray burst, and we've seen a lot of those before. But what was unique about this event, which was animated here, GW 170817, so an event seen on the 17th of August 2017, is that we detected it in both gravitational waves and in optical light. Okay, and that is something that is extremely unique and has happened only once so far. Okay, so how do we study these events and what do we learn from them? Well, gravitational waves are tracing gravity. So they tell us about the masses of the objects, how fast they are spinning, because if a black hole spins, it distorts space around it. And broadly speaking, what I would call geometric properties, things like position of the source and the distance to the source and the inclination angle and so on. Whereas photons tell us about what happens on the surface. Was there any relativistic beaming? How much material was ejected? How fast was it moving? Was there any nucleosynthesis going on? And only by putting all of this together do you actually get the complete astrophysical picture. Okay. Why do we care about this? For example, using that single event, we have been able to get an independent measure of the expansion of the universe. We have been able to put constraints on the equation of state of ultra dense matter. So at the core of neutron stars, the density is about a factor of 2 to 3 higher than the density in an atomic nucleus. Okay, so even things like the Large Hadron Collider cannot probe how matter behaves at those densities, and we can infer it only from these kind of sources. Okay, we can also study the sites of R process nucleosynthesis in the universe. Okay, and I'll come to this again in a slide or two. So basically, with one observation that we have had so far, the first paper that was published by this had 3,500 authors from about 1,000 institutes using about 100 different facilities that studied it. And then in the 7 years since, there have been more than 1,300 papers published about the single source. Okay, it is that valuable to astronomers. You may have heard that we are made of stardust. Okay, so here's the periodic table. And when the universe was created, it started quite simple. There was hydrogen, a little bit of helium, and very, very small amounts of lithium, and that's it. So for life to evolve, for example, you need carbon, nitrogen, and oxygen. And these were actually made in either exploding massive stars or dying low mass stars. So from the hydrogen that the universe started with, the first generation of stars was created. Those stars in their course with fusion generated things like helium and carbon and oxygen and these elements which you are seeing all the way up to about here. And you will have studied this, that binding energy wise, it is energetically favorable to go all the way up to iron. So you can create these elements via fusion, and then that star has to explode, or it has to go nova, supernova, something like that. And that material has to be spread around. Okay, but even after that, you can't actually create things that are down here. Okay, so if you like things like gold, silver, platinum, lanthanides, you cannot actually create them from this. And the way you create those is by actually merging neutron stars. So this happens via a process called R process nucleosynthesis, the rapid nucleosynthetic route. And to our best understanding, all of the gold that you see on Earth was created when some neutron stars merged here a long, long time ago, in somewhere in the vicinity, of course, at astrophysical scales. So I'm not talking about kilometers, but I'm talking about thousands or maybe even millions of light years distance that is involved here. Not millions, okay, thousands of light years. And then the solar system and the Earth were formed from the dust cloud that was enriched by that merger. So if you want to produce some gold, back in the day, the idea was that you could do that by alchemy. So in people would try to do different reactions and try to synthesize gold. But the universe doesn't do simple alchemy, it does ultimate alchemy. So you start with a Big Bang, form large hydrogen stars, and in those stars you synthesize metals. Now, don't tell this to your chemistry teacher, but astronomers are bad at counting, so we count one, two, and many. So we have hydrogen, helium, and metals. For an astronomer, carbon and oxygen are also referred to as metals. Chemists don't like us for that reason. Then you have to blow those stars up and spread those metals around, and that is what you are going to use to create second generation stars. Now, in these stars, you're not actually going to be leaving behind neutron stars from the first generation explosion. So now the second generation stars, you have to kill them again to create neutron stars at the end of the supernova explosion. So if you are keeping track, we have taken some matter, converted it to a star, killed it, converted it into a next generation star, killed it again. Two killings. We still don't have any gold. So now we have to take those two neutron stars together, smash them together, kill them again, this time create a black hole in the process. And as a small side effect of all of this, we just spread some gold around in the universe. Okay, and there's massive, massive, massive amounts of gold that are actually created in explosions like these. So how do we find these sources? Well, there are a number of experiments that are already up there around the world and in India, which are searching for these. So let me show you just a few of them. This is a time lapse of the Growth India telescope in Ladakh. So you can see this beautiful dark sky, Milky Way rising in the background, and this dome in the front is where the Growth India telescope sits. This is the country's only robotic telescope. Reason why I'm taking a detour in the Growth India telescope is for two things. First is that the telescope, of course, is used for searching for electromagnetic counterparts to gravitational wave sources. The second is all the automation of this telescope was actually done by students. So there was a PhD student, one postdoc, and a large number of undergraduates. Today I joined a minute late because we were following up a gamma ray burst where an undergraduate student who's in third year of engineering physics here triggered follow-up of a gamma ray burst that was discovered by the Swift Gamma Ray Space Telescope last night. And we have been following it up with collaborators around the world. So Growth India telescope is one of them. Here's what the telescope itself looks like. Some of you might recognize this from the montage I showed at the start. You can see that the room has only one boring, uncomfortable chair because it is not meant to be sat in. The telescope is completely remotely operated. There is no one in the dome at night. We can control it from IIT Bombay, from IIA Bangalore. But usually we don't even do that. The telescope is completely robotic and it takes care of itself. The other asset that we use is Astrosat. So Astrosat is an Indian space telescope. This is now about 10 years old. And it consists of five telescopes: the ultraviolet imaging telescope. Then the next one is the soft X-ray telescope. We have the scanning sky monitor, the large area X-ray proportional counter, and this instrument called CZTI. So you can also see Astrosat in the background over here. Astrosat has been used for a lot of studies, lot of interesting results and discoveries have been made. You can find more details at the Astrosat website. But we have been using Astrosat to study explosions in the universe. So, for example, we have this is the first 500 gamma ray bursts that we saw superposed on an optical image of the sky. So the points are just showing where the explosions we detected were. And so far, we have detected close to about 700 gamma ray bursts across the universe using this satellite. Okay. Now I told you when neutron stars collide, they emit this flash, and you might see it in X-rays and gamma rays. Unfortunately, Astrosat did not see this burst, although we were sensitive enough to see it, and that has been a problem, right? It means that we could not contribute using Astrosat to this fantastic study, which is so important for us, and we need to fix that. But why do we care about just high energy observations? Why do I want a space telescope to study this? Why not just study it with Growth India, for example? Okay, so what happens with an explosion is that it is going to emit light at many different frequencies, but the time scale over which those emissions happen are actually different. So the high energy radiation that you can see comes within seconds of the merger. So we detected the gravitational wave signal, and just about 1.5 seconds later, we detected the gamma rays from the same source. Okay, and then it starts emitting at lower and lower energies later. So ultraviolet is seen in minutes, optical in hours, infrared in days, and radio can actually take months to peak. Okay, so it means that if I observe using a high energy telescope, then I actually can give the fastest response. I know that something interesting was seen in electromagnetic radiation as well, and that it is something that we should be studying. It also can help us improve the localization. The way gravitational wave telescopes figure out where a source is on the sky is very similar to how you figure out where, suppose you hear the sound of an airplane. Okay, so the way you figure out where that airplane is that your brain can do two processing techniques without telling you what it is doing. It can either measure the time delay between the signals for your left and right ear, or it can actually measure the phase difference if the wavelength is long enough. Okay, and the same techniques are used by gravitational wave detectors. But what it means is, just as if you hear some sound, you can say, okay, it was roughly there. You cannot pinpoint the location exactly where it was on the sky. Gravitational wave detectors can't do that either. But with a X-ray gamma ray flash, you can point out the localization much, much better, which makes it easier for everyone else to figure out where to point and how to study these sources. The third thing is it actually confirms that a counterpart existed. Okay, I've been talking about the event in 2017 and we are now in 2025. Why am I not talking of anything else? And the reason is that there were other neutron star mergers that happened later, but they happened to be further away and there was no counterpart seen. Now, it takes a lot of effort to study these sources in detail. And if I know that there is something worth studying, it is worthwhile putting in all of that effort. But if I'm just going fishing every night and coming out back dry with nothing found, then that actually is not sustainable because the same telescopes have to be used to study the rest of astrophysics as well. So this confirmation of a existence of a counterpart is extremely important. And finally, it also tells us that there was actually something that was allowed to emit light. It means that there was a neutron star that was involved in the merger. It wasn't just two low mass black holes instead of that. And there have been problems about this before. For example, if you look at this one, okay, it seems to be a black hole that is on the lighter side and a neutron star. But if you look at this source, which was also detected in 2019, one of the objects involved in the merger was 2.6 solar masses. 2.6 is heavier than any neutron star whose mass we have measured so far, but also lighter than black holes that we have measured so far. So what was this object? We don't know. But if we had seen electromagnetic counterparts, we would have known that yes, it can't be a black hole because black holes can't emit light. So if this is so important, then who are the people who are actually keeping watch and about all across space, whether there are any X-ray gamma ray explosions that are happening out there? So here are the satellites that have been key in this endeavor so far. Fermi and Integral and Swift and Astrosat were the four satellites that were operational in 2017. Fermi and Integral saw the source, Swift and Astrosat did not. And for both of these objects, the source was actually hidden behind Earth as seen from the satellite at that point of time. Okay, so, and these two finally were launched actually later. So why did we miss the source with Astrosat? And I mentioned that I'll come to this before. The reason is as follows. Okay, this shows a globe. Instead of the globe showing Earth, it is actually showing the sky. And then the burst that was detected by Fermi, it said it is somewhere within this brown patch. The localization that came from the LIGO detectors finally was this. And when you zoom in, you can see that near this galaxy, there was this point source, which was finally detected. So it was located here. Now, Astrosat is what is called low Earth orbit, like many of these other satellites as well. Low Earth orbit is barely 650 kilometers above the surface of the Earth, and that means that the Earth blocks about 30% of the sky. And this circle here shows the part of the sky that was blocked by Earth. And unfortunately, that is where the source was. Okay, so Astrosat can cover about 70% of the sky. There is another issue called the SAA. So when the satellite passes over the South Atlantic Ocean and Brazil, that is where the Earth's magnetic fields are a bit tangled up. And because of that, there is a lot of charged particles that come closer to the Earth's surface, and that increases the amount of background that you see in your satellite. So with this increased background, you have a risk of actually damaging your equipment. And because of that, the satellite, especially the high energy detectors, are typically powered off during that region. What it means is that you are seeing 70% of the sky and you are on for only about 70% of the time, which means you effectively cover only about 50% of the sky. Okay, so we missed this and that was unfortunate. We don't want to be in that kind of a problem again. And in order to solve that, we actually need to build a next generation mission. So what are the requirements for such a next generation mission? Well, the first thing is that we did not see the news sources that came after 2017, and that is because they were further away. It means they were fainter. So we need much better coverage. We need a telescope with a larger area, lower noise, and that can see a larger part of the sky. The second thing that we need is that it has to be a very wide spectral band, because this flash lasts for a fraction of a second. You can't repoint other telescopes to study it. So all the information about the X-ray and gamma ray properties of the source that you want to get have to come within your observations that happened at that instant, which means that you have to study the full X-ray, soft X-ray, hard X-ray, and gamma ray energy range. And the last thing is, you don't want to be unfortunate like Astrosat. So you want continuous all sky coverage. And the way to do that is you take two satellites and you put them on opposite sides of Earth. And that is what will give you all sky coverage. Okay, so it was with these concepts that we proposed this mission called Daksha. Daksha is a fully Indian mission that is a collaboration between various Indian institutes led by IIT Bombay, jointly with PRL Ahmedabad, Raman Research Institute in Bangalore, Ayuka in Pune, and various ISRO centers. And you can find more information about Daksha on this site. And from there, it can also take us to our social media channels. Now, this is a space telescope. It's probably not what you imagined a space telescope will look like. Okay. Now, in brief, Daksha mission is going to use a pair of satellites so that you can continuously monitor the entire sky for high energy transients. Okay. By high energy, I mean anything that is happening in X-ray and gamma rays. So how do we achieve this, and why is it this shape of the satellite? So the way we achieve this is by having a set of detectors. So if I want to study the entire sky, ideally I would just make a sphere and I would have detectors on the entire surface. Now, turns out making curved satellites is not very easy. So you flatten out that sphere slightly. And then you also have to put other stuff in the satellite. You want your communication antennas, solar panels, propulsion, batteries, attitude sensors and things like that. So you need this part which is called the satellite bus. So you have a hemisphere on one side, which is what has the detectors that will be used for this. And we are using three types of detectors here. The first is at low energies, we use something called silicon drift detectors. These have been used very successfully on Chandrayaan 2 and 3. It's the same group that's building them for Daksha as well. In the medium energy range, we have cadmium zinc telluride detectors. These have also been used on many Indian missions before. To get all sky coverage, on this side we have this hemisphere, but on the bottom of the satellite, we actually put four more of these detector packages. And then finally, this is only still covering things to about 200 keV. If you want to study things all the way out to MeV, you need higher energy detectors. Now, high energy radiation actually has very good penetrating power. So that radiation can actually travel through the detectors on the top and make it into the core of the satellite, which means we can actually put high energy detectors inside. And these are scintillators, which also again have been used in a large number of missions by India. And lastly, we have two satellites so that we get all sky coverage. And by putting all of this together, Daksha will actually be the world's most sensitive X-ray and gamma ray space telescope for transients. Okay, let that sink in. We are talking about an Indian mission. It is still a proposed mission. It is in final stages of approval, but not yet fully approved. ISRO is doing what is called a study team as I speak here. Uh, but if this mission is approved and launched, it is going to be almost 10 times better than anything NASA, ESA, JAXA, or any other country in the world has launched before. And this is all going to be Indian. Okay, so here are the four missions that have been active and detecting the most number of GRBs. But Fermi and Swift are actually about 2 decades old. Integral was shut down 2 days ago, so Integral no longer exists. And Astrosat is the youngest GRB mission, but GRBs were not the primary task of Astrosat. There have been some recent missions, actually, a lot of them from China, but none of them are as sensitive or have as much coverage as Daksha. So to give you a comparison, this is something called the volumetric coverage of different satellites, which is the volume of space over which you can actually detect, let's say, bursts like 170817. And for all of these missions, okay, this was a proposed flagship mission for ESA. BAT and GBM are the ones that are the current leaders. Swarm was launched last year. But with all of that, you can see that Daksha has far, far higher volumetric coverage than any of those. Okay, so it's a fantastic mission concept and something that we are working very hard. But just finding these counterparts to gravitational wave sources, do you really need to build a dedicated space telescope for that? Well, that was the driving factor in building this, but that's not the only science that we can do. There's a large number of science cases that Daksha can actually address. Okay, so I'm going to walk you through quickly through some of them. I'll go into detail only in maybe one or two of the science cases. For those of you who are so inclined, here's the refereed paper about Daksha, and you can go read more details in that. Okay, but let's look at specific science cases first. The most interesting to me is basically I'm a kid who forgot to grow up, so I like to build toys to watch things go boom, and nothing goes boom on a larger scale than explosions of stars in the universe, right? So the first thing we want to study is gravitational wave counterparts, and as I told you, we have the best volumetric coverage among all satellites. I'm showing listing a paper here. Bhattacharjee here was Soumyadeep, who was a student from IIT Delhi, who, as a part of his final year work, actually led this study and published the paper. Okay, so students can actually make a huge impact in these fields. We will have the best coverage and ultra wide coverage for studying gamma ray bursts. We will be able to study something called polarization of gamma ray bursts. I told you early on that photons, one of the pieces of information that we care about is polarization. It is very hard to measure polarization of GRBs, and there have been only two missions that have done this for a large number of bursts. One is called Polar, the other is AstroSat CZTI. And we will have better sensitivity than both of them in Daksha in order to measure GRB polarization. So let me go into detail on this EMGW electromagnetic counterparts again. What I'm showing here is for very large number of models. We did simulations about what can Daksha detect and how does it compare to the current world leader in GRBs, which are Fermi and Swift. And I won't go into details, but suffice to note that the Daksha bar is always highest, will detect about 10 events or so per year. And for depending on what model you are looking at, we might detect a large number of them jointly with gravitational wave detector networks. And the volumetric reach is 13 times better than Swift and 5 times better than Fermi. A very, very fun thing that we can actually do as a result of this extremely high sensitivity is we can start looking under the bed for things that LIGO might have missed. Okay, so how does LIGO decide that it detected a gravitational wave event? So it looks for a signal in data, and it has to have a certain signal to noise ratio. And only above that ratio will you call it a detection. Now, how do you decide what SNR is enough? Do you want it to be a signal to noise ratio of 3 or 5 or 8 or 10? And that is finally decided by what is called a false alarm rate. Okay, so LIGO says that I want the event to be so significant that if I switched off all gravitational wave sources in the universe and ran LIGO for or not just LIGO, Virgo, Kagra, everything. If we ran the gravitational wave detector network for a period of 100 years and it was pure noise, all gravitational wave sources in the universe was off, then we want to have only one false event detected in 100 years. So that's the threshold that has been set. Now that threshold translates into a certain SNR based on the fact that I'm continuously looking everywhere. Okay, so for example, if I tell you to find something very elusive, if you're listening for some faint sound and if you keep listening, at some point you'll start imagining that you have heard that sound, very loosely speaking. On the other hand, if I tell you precisely, okay, look only for the next 10 seconds and tell me if you hear something, then there are a lot fewer chances that you will get that false alarm. And that is what we can do with Daksha. We can tell LIGO when to look and where to look, which decreases the search space, and the direction actually helps in correlating and figuring out, let me look events for only that part of the sky. And that allows us to reduce the SNR requirements, which means we can start seeing fainter events which LIGO would otherwise have missed. And we have calculations basically done on this, and there's a project undergoing at Ayuka in this semester, again with an undergraduate student, where what we are seeing is that we might actually be able to double or even triple the number of neutron star mergers that gravitational wave detectors can get thanks to Daksha. And finally, when you are making a telescope that is so much more sensitive than anything that has been flown before, you open up a huge discovery space. You have no idea what the universe does at these levels of brightness because we have never looked before. And fortunately, the universe is quite a fun place to live in, which means that we can be sure that there is some surprise that is lurking out there. We have no idea what it is, but we might be getting something very interesting. Okay, moving on from relativistic transients, we will be able to study compact objects in great detail. We can study things like magnetar flares. Magnetars are extremely highly magnetized neutron stars, magnetic fields that can be 10 raised to 13 or 10 raised to 15 times higher than the Earth's magnetic field. We can also study things called fast radio bursts and counterparts to them. Daksha will have the best sensitivity of any spacecraft for studying those. We can study accreting X-ray pulsars. So these are systems where there is a regular star and a neutron star orbiting each other, and material from this regular star is actually getting stripped off and falling onto the neutron star. And as a result, this thing which is hitting the surface of the neutron star is moving very fast, accelerated by the strong gravity of the neutron star. When it hits the surface, it can heat up the surface to millions of Kelvin, and then it starts emitting thermal X-rays. And there are also sources of non-thermal X-rays. And we will be able to monitor all the pulsars in the sky at all times. So many times when people ask me, how do you study a particular source with Daksha? I answer it by giving the movie title, Everything Everywhere All at Once. We are always seeing the entire sky. Daksha does not point to any given direction in the sky. Okay, if you look at this model that I have in my hand, this is a 3D printed model of the satellite. And if I have a source here, it will shine on this part of the satellite and I'll see it. If I have a source here, it will shine on this side of the satellite and I'll see it. So no matter where I put the source in the sky, I'm always going to be able to detect it with Daksha. We will also be able to study things much closer to home. Okay, so there is something called terrestrial gamma ray flashes. If you have lightning at very high altitudes, they actually emit gamma ray flashes, and we don't fully understand why they happen. And that's important for us to understand thunderstorms and cloud systems and so on. So people have been building instruments to study this. On the International Space Station, there's an instrument called ASIM, which studies this, and Daksha actually has much higher sensitivity than even ASIM. Not just that, the International Space Station is at a highly inclined orbit, and thunderstorms typically happen in the tropical regions, whereas Daksha will actually have an equatorial or near equatorial orbit, so we can study them much better. We can also study solar flares. This is the largest monitor ever built to monitor the sun as a star. For comparison, I'm sure all of you have heard of Aditya L1, which is an Indian telescope that is dedicated to studying the sun. Aditya has a lot of fantastic instruments. One of those instruments is a hard X-ray monitor. Now, Daksha can't do everything that Aditya does, but if you just compare the hard X-ray monitor part of it, the hard X-ray monitor has two CZT detectors pointed towards the sun. Each Daksha satellite will have 80 of them. So two of them put together, we will have 160 detectors pointed to the sun as compared to only two in Aditya for hard X-rays. Of course, we don't do all the other great things that Aditya can do for the sun because we are not a solar mission. Monitoring the Earth, there is actually a very cool technique where if the sun emits a solar flare and that hits Earth, the atmosphere absorbs all those X-rays and gamma rays, but then it reprocesses them and re-emits light as fluorescence. And by seeing what energies the fluorescence happens at, we can, and that allows us to profile the atmosphere and understand the distribution of various atomic species in that. So we can monitor the Earth for this as well. And then a few other science goals, and I'll go into one of them in a bit more detail. We can actually study something called primordial black holes and a low mass range of it for the very first time. I'll go into a bit more detail in that. We can also monitor persistent sources. I said Daksha is primarily studying things that explode in the sky. We can also study some things that are not exploding, and we can continuously monitor those, or slowly varying sources like novae can also be studied. So let's go a bit more into detail into this thing called primordial black holes. Okay, so I'm sure all of you have heard of something called dark matter. It is matter that we know exists. It exerts a gravitational force, but we don't know what it is made of. One of the candidates for dark matter is something called primordial black holes. So at the time of the Big Bang itself, maybe very small black holes were created and they were distributed all across the universe. Since they are black holes, we won't actually be able to detect them using conventional techniques. And if they are lightweight, they are not going to be sucking off a lot of matter from neighboring stars or anything like that. So they won't shine in X-rays and in other wavelengths. The matter that is falling in will not be enough for it to start emitting. So we can study these though using something called gravitational lensing. Okay, so the gravitational lensing concept is as follows. We have Earth here and there's a galaxy in the background and there's a cluster of galaxies in between the two. So this gravitational cluster now has strong gravitational potential. Sorry, this cluster of galaxies has strong gravitational potential, which means that it will bend the light that is coming. So this ray of light was trying to go in this direction, but because of the gravity of this cluster, it got bent and then it came to Earth. Similarly, this light ray would have gone here, but it got distorted and it came here. So now we will actually see two images of the same background galaxy. Now, these images will have slightly different magnifications, which also means that it will have slightly different intensities. So instead of the galaxy, if I now put a gamma ray burst there, then I will see two images on Earth, and the intensities of those two images will be slightly different. Now, instead of thinking of them as images, let us again focus on these light rays coming in. You will note that in this drawing, we have drawn two rays which are hitting different parts of Earth. So if I now have one satellite here and another here, both of them see the same gamma ray burst, they will actually see two different versions or two different images of that GRB. And instead of this galaxy cluster, I'm going to imagine that there's a primordial black hole in between. Okay, so the mass of that black hole is going to decide how much lensing we can do. And we actually, Priyanka Gowde, who just finished her PhD at Ayuka, she did a study on this and showed that we will actually be able to study light black holes. Okay, so on this axis, what is shown is the mass of these black holes in terms of solar masses. And we are looking at 10 raised to minus 15 solar masses. So if you want to think of it in more normal units, that's about 10 raised to 16 grams or so. Now, for black holes, there's something called the Schwarzschild radius, which is the size of the black hole. And for a black hole of this mass, 10 raised to minus 13 solar masses, that's about 3 angstroms. Okay. It means that if I were to try to study this gravitational lensing using normal light, I cannot, because the Schwarzschild radius is much, much smaller than the wavelength of light that we want to use, which means that I have to go to shorter wavelength. If I'm looking at the medium energy detectors for Daksha, the lowest energy or the longest wavelength we can study is 0.6 angstroms. Okay. So the simulations that we did showed us that we can actually detect primordial black holes if they exist. We have something like a 50 to 80% chance to detect primordial black holes of this mass range if they exist. And if we work with some other hypothetical instruments that are, say, orbiting near the moon or so on, we can actually rule out this entire area. So pretty cool things, right? So that was all the science cases that we had for Daksha. Um, Moving on from there, what else is the broader context for Daksha? As I said, there are many institutes that are involved in building this. We will also have a synergy with a large number of other projects. We have telescopes that India either owns or is a partner in radio, in optical, solar monitoring, gravitational wave detectors. Of course, AstroSat exists. We will have synergy with a lot of different international missions as well. There are scientists from all over the country. I have not updated with this map, so there are gaps here, but they have been filled up since. It has been recommended very highly by various Indian studies. There is also a lot of interest from all around the world, by the way. People who have signed up for interest in Daksha science. Um, Status wise, we proposed this to ISRO about 6 years ago. They told us that, okay, your idea is interesting. Please build a prototype. These are technically called laboratory models, and we have actually built laboratory models of all three types of detectors. This is the low energy detector, medium energy, and high energy detector package. We showed that they actually work as expected. And on the basis of this, we are now working towards building engineering models of these systems. And ISRO is now evaluating, saying that, okay, time scale wise, cost wise, and feasibility wise, is this a mission that India should really embark on? We expect that a decision on this should be reached by the end of this year. And then in about 4 or so years after that, we will hopefully be launching the world's best X-ray and gamma ray space telescope. So this is where I'm going to pause on part one of my talk, and let's open up for question and answers and some discussion. Then Professor Shetty requested me to go a little bit into careers in astronomy and a discussion on that. So maybe after half an hour of discussion on Daksha and transients, gamma ray bursts and explosions, we can come back to slides and start talking about these. So any questions?
You may raise your hands if you have any question.
There's quite some discussion in the chat also. There may be some questions in the chat.
Should I read out the questions from the chat?
Sure, that would be.
Okay, the first question that I would like to read out is do the single gamma ray burst give us the information in all the above mentioned wavelengths over time? What you were talking about in the beginning about different wavelengths, and that is where the question came.
Right. So, if you have a gamma ray burst, the burst itself usually is peaking in hard X-rays and gamma rays, as the name suggests. And then we detect for many of them, but not all of them, we detect something called the afterglow. So the gamma ray burst itself is typically bright only in X-ray gamma rays. There have been a few cases where it was nearby enough and bright enough that it was actually seen in optical, for example. But typically the prompt emission, the explosion itself, is seen in X-rays and gamma rays. The afterglow for many has been studied in X-rays, gamma rays, in optical, infrared, ultraviolet, sub-millimeter, radio, and everything. There have been a few gamma ray bursts which have even been seen all the way to tera electron volt energies. So for GRBs, if they are bright enough, we see them at all wavelengths. Um, as far as our theoretical understanding go, they always emit in all wavelengths, but many of them are so far away that you cannot see the radiation across all wavelengths. For example, I talked about a GRB from last night, and that GRB was at a redshift of 2.5, okay, which means that it was a few billion light years away. And that any explosion that, so a GRB in the prompt emission emits more energy in a matter of few seconds than the sun emits in its entire 10 billion year lifetime. Okay, so that's a lot of radiation, lot of energy, but then they're also very far away. So that is why it is not always easy to detect them at other wavelengths.
Okay, there was one more question where the person who has put the question had said it may be, the question may look stupid, but the question is like this. Space is considered as vacuum, right? Then why
Yes.
all these radiations didn't reach at the same time?
Okay, that's not a stupid question. That is a very good question, and that is what people have worked very hard to answer. Okay, so let's start with just the electromagnetic radiation first. And I guess you're referring to the slide where I said that the radiation in high energy comes in seconds and radio takes months. And that has, there are some exotic theories under which that could happen, but that is not what is the cause here. Okay, the explosion basically is a lot of energy injected into a confined space, which makes it extremely hot. And when something is extremely hot, it emits at short wavelengths. As it starts cooling down, it starts emitting at longer and longer wavelengths. So for thermal radiation, essentially that is what happens. A lot of this radiation is not thermal. We have a lot of synchrotron based radiation, for example. And the peak of synchrotron radiation also depends on the average energy of the particle. So if I have an explosion, I start with highly relativistic particles. The jets that are present in gamma ray bursts, can have velocities of 99.999999% of the speed of light. We regularly have detected. So you're probably familiar with special theory of relativity and capital gamma. Okay, gamma is related to beta, beta is V by C. So we have commonly seen gammas of something like 1,000 in these bursts. So these electrons that are present in this jet are highly relativistic. Over time, they slow down as they lose energy by radiation or they collide into other particles, medium, interstellar medium that is present there, and so on. And as they cool down, now their average energy has gone down, so they start emitting at lower and lower energies. So that is why we see these as delayed. Now, the other part is gravitational waves versus X-rays and gamma rays. Okay, the 170817 was located at about 40 megaparsecs. That's about 120 million light years away. So gravitational waves and light traveled for 120 million years and they still arrived within 1.5 seconds of each other. That is the best constraint that has ever been put on the speed of gravity, by the way. But now that much fine tuning is very hard. So what we believe is that there is actually a physical reason that the gamma rays were either emitted late or became visible late. Okay, so there are two possibilities. One is that as at the instant of the collision where the gravitational wave intensity peaked, it started throwing out particles, but then it took a little bit of time for those particles to, for example, collide and start emitting. That is one possibility. The second possibility, which is more likely, is that the particles were emitted in the narrow jet, and the jet, for various physical reasons, spreads out a little bit over time, and that's why emission on the side. We were at an angle of about 20 or 25 degrees from this jet, and we started seeing it late. A third possibility is something called cocoon radiation. A fourth possibility is that there was so much material around that the gamma rays actually got scattered a lot before they came out. We are talking about something like zero point 0.1 solar masses of stuff trying to stop those gamma rays. So there are various physics-based ideas, but trying to figure out why there was a second and a half delay between the gravitational waves and gamma rays is actually something that has kept a lot of theorists busy for a long time. Okay, so this is important. I'm very happy you asked this question. It's not a stupid question. And for all of you who are feeling shy about asking questions, ask them. There are two reasons why you should ask them. First is that without asking, you're not going to get an answer. Second is that there might be others who also have that question but are too shy to ask. So don't feel shy about asking.
Yes, sir. There are some questions for Daksha, and
Sure.
maybe students have got the answer, but still I'll put the question. The question first is, when will it be active? Second, can it help in planetary research somehow?
Okay, so when will it be active is a question based on when it is approved and when we can launch it. What we are hoping for is we can launch in, say, 2029. The mission is being designed with a nominal 5-year lifetime, but there are no consumables on board, which means that we can actually operate for a much longer time. For comparison, the cadmium zinc telluride detector on AstroSat. So this is a model of AstroSat, and this green box, not green in real life, is representing the cadmium zinc telluride imager. Over 9 years of operation, its performance has degraded only by a few percent. So if you extrapolate linearly from that, which is not a great idea, but if you do, then we can last for a few more decades. Okay. What limits the lifetime of a spacecraft? It is usually after that stage some kind of a catastrophic failure. Some component breaks because of high radiation in space, or maybe there is a micrometeorite hit which actually physically punctures your satellite or something like that. Uh, the other problem in low Earth orbit is that at 650 kilometers, the Earth's atmosphere is extremely thin but is not zero. So you are still colliding with air atoms, and that makes you lose your velocity slightly, and over time it comes down. A large object like the International Space Station, which is at some 500 kilometers above Earth, actually decays by tens of kilometers every year, and it is regularly reboosted up. So that would be another limiting factor in the lifetime of Daksha. Planetary science studies, yes, we will study a planet called Earth, but unfortunately, we can't study any other planets. They are not bright in X rays and gamma rays. But Earth, as I said, atmospheric studies, terrestrial gamma ray flashes, sun-Earth interaction, these kind of things can be studied with Daksha.
Someone also wants to know the budget of Daksha project.
The project budget is something which is not yet fully known. That's part of the things that ISRO is working on, because we have to figure out whether we can launch both the satellites on a single rocket or not, whether we want to make both of them together or one at a time. That changes the cost. Making two of them together is cheaper, but of course is more expensive than making just one of them. How many other piggyback launches can we get on the rocket and things like that? So the full budget right now is not known. There is a range of numbers which I should not be saying right now, but what I can tell you is that it costs less than a single team at IPL typically. So that's your reference point.
Good point, sir. What and how will be the career in theoretical astrophysics?
We will come back to that in another 15 minutes maybe, and I'll spend a good half an hour on careers in astrophysics.
So the next question is how to increase the precision of LIGO detectors, as increasing the length of arms of detectors is not always feasible.
Correct. So, good question. I'll start with some context. The name officially is LIGO Aundha. Before that, it was called LIGO India. Indigo is not the name of the project. Indigo is the name of a group of scientists who are interested in gravitational waves. This has been confusing, but just for clarity, 2 points. One is it's not pronounced LIGO, it's pronounced LIGO. Nobody here called it LIGO, but many people often do. So it's called LIGO, and the name is LIGO India or LIGO Aundha. We are designing LIGO Aundha to be as sensitive or more sensitive than our two counterparts in the US. So there are two identical detectors, LIGO Hanford and LIGO Livingston in the US. There are two different detectors, one called Virgo in Italy and one called Kagra in Japan. We are building ours to be identical to LIGO US. Okay, and with that, what we are doing is trying to put in better technology, mirrors with better coating. So LIGO is an extremely high sensitivity, extremely high precision instrument, and I'm going to take a little bit of detour here into telling you what kind of noise sources we have to worry about. Okay. Um, I'm sure all of you at some point or the other have attended a very loud party. Shadi Ka Barat, Ganesh festival is also acceptable thing instead of a party, right? And if you have loud band playing next to you, you can actually feel the vibrations. Now that is you as a human just sitting there. You can feel things move. Those of you who are staying in hostels, if you have neighbors who play loud rock music, you will have seen that your bed can vibrate. Any of these are noise sources, because with LIGO we are trying to measure small vibrations. So problems that have been detected in LIGO US, there was a crow who was pecking on the surface of the tunnel. Inside the tunnel is an air gap, inside that is a vacuum tube, and inside that is the laser. But those vibrations coupling through the ground actually were getting detected by the detector. So they had to arrange for a different water source for that crow so that it did not actually bother the observations. In Louisiana, in a certain season, when they start cutting trees, every time a tree falls in the forest, we actually detect it in gravitational waves. There was a stand fan in the control room of one of the LIGO centers, and that fan was old, so it vibrated a bit. You'll again शादी में देखा होगा drrrr करने वाला fan होता है. Those vibrations were getting detected, and this is after 4 stages of state-of-the-art seismic isolation and things like that. So we are trying to measure very, very tiny effects. What else do we do? If a single particle that falls, a dust particle inside the LIGO tube, can actually break the detector lock, and it takes half an hour to reset the detector after that. Um, Effect being measured at this stage is so small that we are actually using something called squeezing of light. Okay, there's a quantum mechanical effect. You have all heard of Heisenberg's uncertainty principle, which says that at its base saying that position times momentum uncertainty can only be so small, but it does not actually say where the uncertainty has to be. So squeezing, roughly speaking, is trading off the uncertainty in the momentum of the photons along the direction of travel. By increasing the uncertainty in the other two directions, you can actually get more precise measurements. And that is the effect that is being used right now in LIGO. Literally, this instant, it's being used in LIGO. The coating on the surface of the mirror the quality of that coating and the thermal vibrations of the surface are something that are becoming a problem, and that is being improved. So these are the different techniques that are being used to improve the sensitivity. There are next generation projects like Cosmic Explorer and Einstein Telescope and so on, which will actually try to build longer arms. That not just makes it more sensitive, but it also changes the wavelength and frequencies at which you can study gravitational waves. So those are other techniques.
One participant, I think the name given is Ajay Mehra, he has said, I'm currently studying GRBs from 1 month around. Can you suggest some materials or resources where I can understand how to read data from Swift or other place? What more study I can do in GRBs? Can you provide resources related to GRBs?
Okay, so GRB resources, both Swift and Fermi have things called cookbooks where they actually explain how to analyze GRB data. Last year, we conducted a workshop at ASI, and the material from that is available online where it has a little bit of tools on analyzing GRBs, but they're very basic. Just as you are doing a Python school right now, we have conducted something called Growth Schools. Growth is our international collaboration, which stands for Global Relays of Observatories Watching Transients Happen. Okay, quite a mouthful. We conduct schools every year. Okay, and after Growth, there are now ZTF schools which do the same thing. And we have created Python notebooks, very similar format to what you guys are doing right now, because we use the lessons learned from that in this workshop which you are doing. So we have recordings of that available online. So if you search for Growth School, you'll find those. And there we have one of the sessions was on X-ray gamma ray data analysis. So you'll find some things there as well. For reading up about GRBs, there are a few good textbooks. There's one by Andrew Levan. I think there's one by Bing Zhang. Those would be good ones to read. See, anytime you are exploring a new topic, uh, you first start by trying to find a lecture about it online. That's a good place to start. Read up Wikipedia and so on. Decide if you are interested in the topic. If you are, then you should go looking for a textbook. That's the most reliable way. When I'm saying watch a lecture, make sure that you are getting a lecture from a good source. Especially in astrophysics, there is unfortunately a lot of crackpot material on the internet. Anytime someone starts by saying, here is how I can prove in 5 minutes that Einstein was wrong, that's a good time to switch off that video.
Next question. If the Earth comes in between a very high intensity gamma ray burst, then what can be the consequences faced by humans and the Earth itself?
That is interesting. It depends on how far away we are. If something like the sun exploded as a GRB, it can't. Sun is not heavy enough to have a supernova explosion at all. But then all life on Earth would die. Okay, but I'll give you a example of something else. Okay, there's a gamma ray burst that happened about 2 years ago in October 22, which was the brightest GRB that we have seen. People jokingly call it the boat, just as you have GOAT for greatest of all time. This one is called boat for brightest of all time. That GRB was beamed towards Earth. If it's not, we don't detect them. And the intensity of the burst by any standards of energy that you have for normal life was quite low. Okay, astronomers use CGS units instead of SI, and the intensity was 10 raised to minus 2 ergs per square centimeter on the surface of the Earth. So that's very low. For comparison, can anyone tell me what the solar constant is? How much energy do we get from the sun per second per square centimeter? So it's a kilowatt per square meter. Okay, I'm actually going to do something interesting here. Okay, I'm going to share my screen again. And I'm purposely going to work this out in front of you. So let's open a window. Because you are all doing a Python workshop, I'm going to launch interactive Python here. Uh, can you all see this?
Yes.
Okay. So I'm going to say %pylab. That actually imports a lot of numpy and other things. I'm going to say import astropy.units as u. Okay, now solar constant equals 1 into u dot kilowatts divided by u dot meter square. That's the amount of radiation that I get per square centimeter per second. I have not put the per second here. I can if I want to. So, and now I want this in CGS units. So I will say solar underscore constant dot 2 u dot erg by u dot centimeter square per second. Okay, and that is, oh, sorry, my bad. You see the mistake that I did? I used
Watt
kilowatt
was already having.
and that already had seconds. So I'm going to redefine the solar constant here without the seconds. And here it is, right? So the sun gives us 10 raised to 6 ergs per square centimeter per second. This GRB, because it was very far away, actually gave us 10 raised to 8 times lesser energy. But despite that, it was actually detected in the ionosphere. Okay, so people who are monitoring the ionosphere for radio studies of the sky, um, just by the sky, I mean atmosphere, they actually found that the GRB changed the ionization in the ionosphere. It changed the plasma density, which changed the reflection of radio waves through the atmosphere. And that's for a burst that's still far, far away, happened to be bright, happened to be pointed at Earth. Okay, so if there's a GRB nearby, then it can actually have enough radiation that despite the atmosphere trying to block that radiation, a lot of it will make it to the surface. And if it is very close by, then it could unfortunately end all life on Earth. Now, if you take the rates of GRBs in the universe and how far away it has to be, well, it turns out it needs to be in our galaxy. Then you count the number of such explodable stars in the galaxy and the probability of Earth being among the jet beams and so on, and that's negligible. So there's no real risk from it.
Can see hand raised. A Wilson College person, maybe Professor Michael. I don't know who that person is. Will you please unmute yourself and ask
Shubham.
your question?
Hello, good morning, sir. Good morning, madam. Madam, I'm Shubham. Yeah.
Okay, Shubham.
Sir, yeah, I had this question about LIGO.
Mm-hmm.
Uh, so when gravitational waves interact with LIGO, so the distance of the two arms changes.
Correct.
This change is because of the change in the space
Correct.
fabric.
Correct.
And again, the light also travels on the space fabric. So
Correct.
why should there be like
That is a very good question.
I
Okay.
mean, shouldn't it also
Correct.
travel along the curve and
Correct.
effectively it should be a
Correct.
destructive interference all the time? I mean, why is
Uh,
it going through the
correct.
space-time fabric?
Correct. Right. So the question basically is that um, light is traveling through the same space where the detectors are located. If the detectors got stretched, then the light should just have been stretched with it. The answer of that goes into a little bit of mathematics. And if you pick up gravitational waves textbook, for example, there's a good textbook by Sanjeev Dhurandhar and Sanjit Mitra. Or there are a bunch of, there's a book by Bernard Schutz. There are papers about it. They will actually go into the mathematics of why this happens. It is a subtle answer. I don't think I can explain it very quickly here, but that's a great question. The short answer is that yes, that to first order, what you're saying is correct. But when you go into the details of how the light is moving and the fact that we are getting multiple reflections, all of that put together does still give you a residual signal.
So there are many more questions. Would you like to take them right now or
So
at
we
towards
have
the end?
two options. I will ask you and maybe Mahesh sir to decide. We can go back and talk about careers a little bit and then open up to questions about careers and this together, or we can continue with more questions about this and go to careers later. I'm okay with either.
Myself, will you please tell me what should we do? I can.
Okay, if there are lot many questions coming up now, then better we start about the career things and then we can take more questions later.
Yeah, I think there are some 16, 17 more messages over here. So let us take all these questions towards the end then.
Okay, sounds good.
Thank you, sir. Continue.
All right, so coming back and going back to PowerPoint, we were here with Daksha. And let's move on now to astronomy careers. Okay. Um, Yeah, a lot of you might have been thinking about your interest in physics and astrophysics and wondering whether this could be a good career option for you. Um, so the first question is, should you make astronomy a career? The second question is, what is the difference between astronomy and space science? And after answering both of these, I'll try to go into whether you should, how you should go about it. Okay. So the first question is, should you do a career? And that's a very personal choice. Is a career in astronomy and astrophysics a good idea? For me, it clearly was. I am doing it, right? But that doesn't mean that everyone should. And that depends on your interest and aptitude, both. So think of it this way, okay? If you take a generic example, if you take cricket, okay, most people in the country say they like cricket. And if you ask them, would you like to be on the Indian cricket team? A good number would say yes. Then if you ask them if they are willing to put in, or will they really put in all the effort it takes to make it on the Indian cricket team, a lot of people will think they will, but then they actually will drop out through the training program. Okay, so a similar thing applies here as well. If you want to do a career in any field, you have to be really good at that field. And you have the ability to be good, but you have to be willing to work very hard on it. The other part that comes in is that really something that you want to do? For example, I like listening to, let's say, music, but I'm really bad at it, at playing music, and I don't have the patience to actually practice to become good at it. So I'm not going to choose music as a career. I'm going to keep it as a hobby. My hobby will include in a typical, so I'm from Pune originally. So in a very typical Puneri style, my hobby will include claiming that the musician is really bad and I understand his or her music much better than them. But both the listeners and I know that this is not true. Okay, so similarly, if astronomy is a hobby, if you like stargazing, if you like astrophotography, that is not what I do as a professional astronomer, right? It's been years since I've actually looked through a telescope, for example. I operate one of the Indian telescopes. Myself and Sudhanshu Barve at the Indian Institute of Astrophysics are in charge of the Growth India telescope. We are taking data on it regularly. I'm working with international collaborations, but I don't get time to go stargazing anymore. So if stargazing is what is driving you, for instance, then my career choice would be clearly a bad idea. Okay. And this is something which you really should keep in mind before deciding whether you want astrophysics as a career. It can be a great hobby while you're doing some other career as well. This is not to discourage you from trying anything. All I'm saying is that you have a lot of interests in life and you will have one career. So every interest does not need to translate into a career choice. The second part is that a career in astronomy and astrophysics and a career in space science are different. Space science, broadly speaking, is about putting things in space. So it's about rockets, satellites, human space flight, Indian space station. So for example, if you are operating a cable TV channel and you want a satellite to be able to broadcast that to everyone's dish TV, then you are going to be working with space scientists. And as that person, you may have absolutely no interest in stars and galaxies and anything else. Astronomy, on the other hand, has to do with studying stars and galaxies and planets and cosmology, formation of the universe, interstellar medium, exoplanets, and all of that. That has very little to do with space science. The only intersection with space science comes with things like this when we want to put telescopes in space. Okay, but a majority of astronomers don't actually work on putting those telescopes there. They work on using telescopes that are in space or on the ground, or they work on theory. So all of this is a distinction that you should keep in mind. If rockets are what excite you, then you should be looking into space science as a career and not astronomy. And I'm going to talk about astronomy and astrophysics today. Okay. Um, so with this distinction now, where do Indian astronomers work? Broadly, two categories of institutes. One is what I'll call research institutes. So these are places like TIFR, IUCA, NCRA, RRI, IIA, ISC. These are institutes which are set up completely for research. Places like Aries, Nainital, IIA, Bangalore are fully dedicated to astrophysics. Aries also does atmospheric sciences. Other places like IISc or TIFR study a large number of various scientific disciplines. On the other side, we have educational institutes. These are institutes which also have an undergraduate program. I should probably now shift IISc to this side. So these are places like IITs. I've named only a few of them here. These are places where there are astronomers, but this list is not complete. There are astronomers in a lot more IITs and a lot more IISers. For example, IIT Hyderabad has a few of my astronomy colleagues. Other IISers also have people, but IITs and IISers have now come largely into in a large way into astronomy and astrophysics as well. IIST Bangalore, Indian Institute of Space Technology, not Bangalore, Trivandrum. I made this slide while I was half sleepy last night. Sorry about that. IIST is in Trivandrum. They are mainly into space science, but they also have astronomers. And then several universities, Delhi University, Pune University, Raipur, Christ, many of these places also have active astronomy and astrophysics groups. Okay, so if you are looking for higher studies, PhDs, and so on, these are places you could consider. There are, of course, a large number of places abroad as well. What is the typical path that an astronomer takes or should take? You start with your 12th physics maths. Most of you are probably in this phase right now where you are doing BSc physics or engineering physics or something like that. You go on to do your MSc and then you follow it by a PhD. So if you want to be a professional astronomer, going all the way through to a PhD is extremely important. If you terminate your education here, then you are not going to be able to be a professional astronomer. There exist alternative routes. For example, after BSc, you can go for an integrated MS plus PhD, or some people go directly from here to here with an integrated BSMS program that's quite popular these days. You can also go from a BE or a BTech, but that is not recommended. It is possible to do that, but going back to our cricket analogy, it is like saying that I want to be a professional cricketer, so I'm going to go and study, learn how to play badminton first. Right? Clearly a bad idea. So if you want to become a scientist, why are you starting with engineering? I'm one of the people who started with this bad idea where I actually did a BTech in electrical engineering. I did manage to come back into astrophysics, but there are a lot more examples of people who couldn't actually make this transition. Okay, so keep that in mind that this route, while possible, is not strongly recommended. After a BE, you could also go into integrated MTech plus PhD. So there is one scenario where this route is actually a good idea, which is so when you think of an astronomer, you typically first think of observers, okay, people who are using telescopes to study things. If I ask you to name astronomers or astrophysicists or famous scientists in general, you are actually more likely to name theorists. You would name people like Jan Narlikar or Stephen Hawking and so on. So apart from theorists and observers, there's a third group of astrophysicists, small fraction, who are people like me who build the telescopes that astronomers use for actually studying the universe. So if you want to do instrumentation, in that case, this is the recommended route because you do need to have the engineering background, which will help you actually accomplish these goals, actually build instruments, understand them well, build cutting edge latest stuff. What comes after the PhD in astrophysics? Typically, you go and do a few years of what is called a postdoctoral fellowship. And after that, you apply for your permanent jobs. You either can become a professor in a university, so places like IITs or universities, as I said. You could become what is called a research faculty or a full-time researcher. So you go and join, say, TIFR. Or there are some posts that are coming up in India for research scientists where you do not actually even take. So here for example, in my group, I have 6 PhD students, one of whom is actually joining tomorrow, so 5+1. Then I have a large number of undergraduate students, and then I also go and teach regular classes. I go and teach, bachelor's and master's students in regular coursework. At a place like, say, TIFR or Ayuka, you don't have undergraduate teaching responsibilities. So you do take PhD students, you can take masters and undergraduate students for projects if you want, but that's up to you. Research scientist, you will not be taking students at all. There are limited places like this in astrophysics, but if you in other fields of science, if you have heard of places like CSIR, NCL, and so on, that's where all the research scientists are. This is the conventional path. By no means is this the only path that you should be taking. For example, you could go and take up teaching positions. All the faculty members who have been coordinating this course, A lot of them went through routes like this and got into teaching positions. There is also a lot of options available now for going into industry. If you ask at the end of the day, what is a PhD? What you are doing is you are taking a problem which no one has ever solved before. You are spending 4 or 5 years attacking that problem from various angles. And at the end of it, the PhD certifies that you are among the world's experts in doing that kind of thing. So starting from a problem which was very hard to tackle and very few people could do it, you go all the way to being one of the world's experts in that. Now, when you think of it that way, that is a very valued skill for industry. If you are trained, for example, as a part of your astrophysics PhD, you will do a lot of data analysis, you might do coding, you might do instrumentation, and you are trained at working on a difficult problem for a long time until you finally solve it. Industry absolutely values that. So there are people with astrophysics backgrounds who have gone and worked in various companies. One of my friends, for example, after doing a PhD in astrophysics, has worked in Google, Facebook, Airbnb, and is now working in Instagram. Okay. So all of these options are available if you want to go that way. And now I'll spend a few minutes talking about what makes a good PhD application. Okay. So there are many components to your application. The first, of course, is your academic transcript. What courses did you do and how well did you do them? Okay. Some places ask for a transcript, others don't, both in India and abroad. Um, if I'm looking for a student, I want to make sure that they have a solid foundation. Okay. Now, in what I'm going to say for the next few minutes, I'm going to focus primarily from my perspective. So whatever I'm saying is strictly true for say admission to my group and IIT Bombay, but is applicable to most groups around the world. Okay. So I'll keep saying I, but it means most people. So what do I want in a student? Um, so suppose in this course that you are doing, you are told to do group projects instead of individual projects. You are going to start looking for teammates, right? And what would you want in a teammate? You would want someone who has actually understood the subject matter, someone who actually is interested in the subject matter, someone who's willing to work hard, and they are not going to disappear, say 2 weeks down the line, suddenly leaving you stranded in between. Right. So when I'm looking for a student, I'm looking for the same characteristics. During a PhD program, in the first year or so, it is completely time spent in teaching you from your faculty and a group, from your advisor and a group. They are going to spend in a lot of time and effort in teaching you what needs to be done. Once that is done, the next thing is that you start working on some analysis and so on, and then you are kind of in a neutral zone. And then in your fourth and fifth year is when you are actually actively contributing to the group. That is when the group as a whole gets returns on their investment, so to say. So when we select a PhD student, when we are going to invest all of this time, we want to make sure they are in it for the long run. How do you convey that? You convey that by convincing me that you really have thought about this and are interested in astrophysics. We get a large number of people who say, "Arey, wo Discovery पे documentary देखा and now I want to do a career in astrophysics." This is equivalent to saying Three Idiots देखा and that's why I want to join IIT. Okay, just as you wouldn't go to Bollywood for your perception of what college life is, how many of you have your college life that is exactly like Karan Johar movies? Anyone raise their hands? Yeah, I thought so. Similarly, documentaries on Discovery Channel don't necessarily tell you what professional astronomers do. Okay, keep that in mind. So I'm looking for someone who has a solid foundation. Now you're students, you won't already know. Suppose I'm wanting to hire a PhD student to search for gamma ray bursts in Daksha data. Okay, you're a student. I don't already expect you to be an expert in gamma rays or in Daksha data analysis or anything like that. What I do expect is that you have the basic skills which will make it possible for you to learn these things. That typically means we want to see a good performance in all of your physics courses and your maths courses. Not the advanced abstract mathematics necessarily, but depending on what part or what subfield of astrophysics you are working in, we might need you to have a good grasp on calculus or complex integrals or in general partial differential equations, statistics. Okay. And in physics, again, depending on what area you are wanting to work in, I might need you to have a good background in classical mechanics or optics or quantum relativity, and that is reflected through your transcript. So that is number one. Number two is that if you come to me saying I was born to do astrophysics, but I started doing it only yesterday, I'm going to have a hard time believing that. Okay, so it means that it helps a lot if you have actually done projects. These projects can be done in various forms. One way to do it is just work with the faculty in your college. If you are lucky enough to have astronomy faculty in your college, go do a project with them. The Indian academies, the NASI, INSA, and IS, together have this annual internship program, and that is the best opportunity to go get internships. So apply for that program. They will try to pair you with a professional astronomer somewhere if you get selected, and that will give you a chance to do this project. Now, not all of you will get those opportunities. That is not the end of the world. If you say that I self-studied and did this project, so for example, I have my website here on every slide. If you go here, then there are tips for students where I've shared a whole bunch of resources. Uh, if you go and do any of these online courses, for instance, so there are courses on Coursera. There is an excellent lecture series that Professor Srinivasan actually conducted for the Astronomical Society of India, a set of 41 lectures that covers all topics in astronomy. On the Government of India Swayam portal, there's a course on astronomy and astrophysics that Ayuka, with help from many others, put together. Astronomers, experts from all over the country were called in, and all those lectures are available on Swayam. So if you go and complete any of those courses and put it on your resume, even if you don't have a certificate, that is still better than not having anything. So suppose some student applies to me and says that I've done these courses, it will make that application look interesting to me. Of course, I can't blindly trust it, right? Anyone can say that I've done these courses. But if other aspects of your application are good enough for me to invest time in it, then I will talk to you. I'll set up an interview and talk to you. Uh, so will many others. And it is very easy for us to figure out who's lying and who is serious. Okay. In every application season, I easily get at least 100 internship applications. And over time, we've become really good at screening them. And a lot of them we can actually see are very generic applications where and all the tricks that you can imagine we have seen, by the way. Okay, I've seen people who look at the website for 5 seconds and apply, saying that, oh, I'm very interested in neutron star studies and your area of research. 2 years ago, I was getting a lot of applications saying I saw your recent paper on GMRT and was very impressed by it, which is extremely comedy because I had not written that paper. There was some other Bhalerao who wrote that paper. And I started wondering why people are writing to me saying that I was impressed by your paper on GMRT. It turns out Google Scholar was wrongly giving that as a top result. So all of these tricks, remember that your faculty have been students in the past, and we remember what it was to be a student. Okay, so we can also figure out if you have actually written your application or if you got some large language model, ChatGPT or Gemini or something else to write it. It's very easy to see. Um, Okay, so that is your second thing, which is that if you have had an opportunity to do a project or some serious self-study, then do it and mention it. So workshops like this, or LIGO, for example, has something called a LIGO Open Science Center, where we have tutorials for doing gravitational wave data analysis. If you really like gravitational wave data analysis, go do those tutorials. And then when you write to someone who works in gravitational waves, they will say, okay, so and so is serious enough that they went in and put in the time and effort to do this, and they are capable enough that they could complete it. Similarly, the growth schools is another very nice set of notebooks that are available online. So do use those resources. The third thing then is you have a statement of purpose. Okay, and the statement of purpose is something that students actually freak out a lot about. Part of it is because that is the only thing that you can really control during applications. Suppose you get up today and say that, okay, I'm going to start applying to various places. You cannot change your academic background. You cannot suddenly do a project night out market and tomorrow you will have a result of that. But you can hope that you can write a magic SOP by tomorrow. That is not true. Okay, I've never students as a student I had heard of this miracle stories where someone wrote a statement of purpose that was so impressive that they were given a red carpet welcome. In practice, I've never seen that happen. Okay, so statement of purpose is important because it's the only free form part of your application where you can tell me your story. So suppose in my case, for example, I was an engineer who was claiming that I want to spend the rest of my life doing astrophysics. One natural question that comes up is, how do I believe you? Right? Which means that how do I know you are good enough to do this? And how do I know that you are actually interested as opposed to having a sudden crush on this field from yesterday onwards? So in my SOP, what I did was I conveyed where my interest in astrophysics came from, how I have actually nurtured that interest through my studies. So although I was doing engineering, I did a bunch of projects with different people on astrophysics. What have I studied? What is the background knowledge that I have? And all of that is what I want you to convey in your SOP. One thing not useful to do in your SOP is simply write it as a verbose description of my CV. Okay, so if your CV says that you did your 12th standard in so and so place, you were a board topper, then you joined so and so college, you are doing a BSc with specialization topic in this, and you are doing a MSc in this, I can already read all of that in your CV. If you just write down the same thing again and again, just using more words in your SOP, you are wasting a good opportunity. So instead, use your SOP to tell me what it is that you would want to do in the future. How will you working with me for a project or for a PhD make it impact your long-term career? How is it that you, with whatever background you have, are actually trained to do this? What are the lessons that you have learned? Um, there are also people who have different preferences about selecting students, and that's something that is important to keep in mind. So, for example, I've heard of cases where students would like to say that I've never failed at a project in my life. I've completed everything. And I've heard from faculty members that they actually reject some applications. Not all, but you would think that that's a good quality to have. But some faculty members commented that they will actually reject such an application because nobody is an absolute genius. And at some point, when we push you hard in your PhD, right? Because as a PhD advisor, my job is to make you a fantastic researcher, a fantastic scientist. So I will push you hard. I'll make you work on things that are difficult, that are complicated. And what people have said is that at some point in that, you will fail. You will come across something which you cannot accomplish. And if you have never failed before in life, then they are worried about how you will handle it. Will you just break down and stop working? We don't know. So I don't share that view. Okay. But there exists. So you have to keep this in mind that there are preferences that vary from universities. There are departments that will admit you to a department and assign you a guide later. There are cases where you are directly selected by a person for working with them. There are cases where you join a group and decide your project later. There are cases when the funding is already tied to a project and you're hired to work on a certain thing. And all of these variations are a part of life. Whether they're fair or not is an irrelevant question. Okay. One example I can give from a few years ago is that I had a great student who had a good rapport with one of my colleagues abroad, and there was a very good chance that the student would get a PhD admission in that university. However, the year before that, a large number of students joined that university, and the university decided that this year they are going to take zero PhD students. So even if this student had been the world's best student, he was good, he was not the world's best, but even if he had been, he would not have joined that university because they just decided not to take anyone. In my own case also, I was uh, I for four schools that I applied to, I was rejected by three schools and accepted by one. The one that selected me actually had a higher rank than the three that rejected me. So there are variations that are completely beyond your control. And unfortunately, the best thing that you can do is prepare and apply to multiple places so that you are increasing your chances. Now that brings me to a next point, which is that there's a large number of people who just blindly apply everywhere, and that is outright stupid. Okay. Um, if you indulge me for a moment, think of this as an arranged marriage. Okay, रिश्ता लेके जाना है तो you first do homework about कहाँ रिश्ता लेके जा रहे हो. You don't blindly start walking around and knocking on every door, seeing if there is a suitable marriageable age partner available. Similarly, whatever university you are applying to, you should actually study about that university first. See what people there work on. Are they interesting? See if you can get in touch with some student who's working there and talk to them. If you write to some DC student there, they'll usually be happy enough to respond to you, even if you're writing abroad. Within India, if you find students listed, then you might even be able to find someone who's from your college studying at some place. Talk to them about what PhD life is like. Okay, talk to them about what working at that university is like. Um, One more suggestion which is useful to keep in mind is try to find a place which has multiple interesting people, not just one. Suppose you join a place and that person and you don't end up being compatible with each other, right? Someone who is a great scientist might just have a very different style of working from you, and you might not be a great team. In that case, it was nice to have some other options open. One of my friends joined one university, could not get along with her advisor, and as a result had to move from astrophysics to a completely different field because in that university there was only one astronomer. So that's not always a great idea. Okay, so study what universities are of interest to you and apply to a select number of places. 10 is a good number. Okay, if you start applying to 100 places, and I've seen students who do, it greatly dilutes the quality of applications. And we can again tell, remember, we are looking at hundreds of applications regularly, so we can easily tell who's serious and who is not. So don't make that mistake. The last part is that letter of recommendation is also an important part of your application. Again, some places ask for it, some don't. Lot of students simply try to get a letter from the senior most faculty that will write it for them, and that is not a great idea. Okay, just because a letter is from the HOD or principal of your college doesn't mean that it is a more valuable letter. What I'm looking for in a letter is that I want to see the faculty's impression of you and I want to see concrete examples. So get a letter from a professor who you have worked closely with, who you have had a good rapport with, and will actually write good things about you in that letter. For example, every letter will say, yeah, XYZ is a good student, they work hard, they attend classes. Every letter will say that. It's not going to make you stand out. Okay. What will make it stand out is that if the professor says something like, out of my class of 50 students, she was the one who would actually interact most with me in class, would always have insightful questions. She once caught a mistake that I made while writing on the blackboard. Concrete examples, which could be of even small interactions, are going to be important. Or he was my student in this project and he actually did a lot of literature survey and reading, which other students had not done. He actually came with a lot of background information, was always asking doubts, working very hard to make sure he understood stuff. He was not great at coding when he started working on this, but he learned programming as he went along, has improved drastically. Concrete examples of what you have done are what matter in the letters of recommendation. So get letters from faculty members who have actually worked closely with you. That is the most important thing. It's okay if they're course recommendations, it's okay if they're project recommendations. Brand name doesn't matter, content matters. Okay, so I will stop here with that and we can go back to interactions.
Thank you, sir. So should I take the questions again?
Yes, please.
Okay. So we stopped at one point. Now I will take the next question. Can we use any other instruments or techniques other than interferometer?
I actually have a request. Let's look at application related questions first.
Okay.
And then if we have time in the end, we can go back to questions about the science side, maybe.
Okay. Okay.
Okay, so there's a question that I see here, which is another common thing that students believe, which is there's a question from Neha saying that I worked on GRBs and I'm applying for PhD. It is the only topic and I'm having difficulty in finding other topics. As I said, you are students. So if I am looking for something to work on GRBs, someone to work on GRBs with Daksha, I don't expect them to already be a pro in studying GRBs. Okay. A project that you do as an undergraduate uh, is a very strong function of what opportunity you got. So if you started working on GRBs or exoplanets or anything else, it is more likely that you worked on it because it was the only non-boring topic that was available to you, as opposed to you carefully exploring the entirety of astrophysics and deciding that this is what I want to work on. So in your SOP, if you say something like, I've done a project on GRBs, I liked it, but now I'm keen to explore more of astrophysics, then that is a perfectly acceptable thing. My PhD was on studying neutron stars and was on building a X-ray space telescope called NewStar. I had not done any of this as a part of my undergrad. Okay, and that doesn't matter. I had done projects, they were on other things. I had done a project in radio astronomy. I've never done radio astronomy since. Okay, so it does not matter that you are not an expert in the field that you are applying to. A project, a completed project is extremely important demonstration of the fact that you understand what research is and are willing to put in the effort to actually complete something. Okay. Um, some of you may have done courses in which you had a project component. Okay. I'm not talking about your usual labs. So when you go to a typical BSc lab, there is one experiment, some chemical reaction or whatever that you are supposed to do. And that you go and do it, and there's a standard result that is available. You compare against that and you are done. Okay. As opposed to that, if you have actually done an open-ended project where someone asked you to build something, demonstrate something, you will have noticed that it is much harder than you think it would be, right? And it doesn't work, for example, when it was working yesterday, but today in the demonstration to your prof, it doesn't work, right? So there are a lot of things that we think are done and complete or straightforward or easy, and they are not. So if you are doing a project, a research project, for instance, then uh, taking that all the way to completeness is a lot more difficult than just doing it as an exercise as a part of a course. And if you could take that to completion, then that shows me that you have the tenacity, the background, the skill set to actually do research. So it then doesn't matter too much what your research was in as an undergrad. You can broadly apply to any other area as well.
Sir, I went through all the questions and
Hmm.
I suppose you have answered most of them already in terms of how to select a particular institute, how to write uh, the CV or the proposal, and how to decide on the project guide. I mean, how to decide with whom to work and all these kind of questions, which I think you have already discussed in detail. So most of these questions, according to me, you have answered.
Great. Okay. So one more thing that as I was scrolling through questions, how do I select what do I want to do my PhD in? Okay, that's hard. And it sounds impossible, right? So imagine that you have gone to some fancy wedding where there are 10 different buffet counters serving 10 different cuisines. You walk in, there's a chaat counter, then there's a pav bhaji counter, then there's a South Indian counter, North Indian counter, Chinese counter. Now, if you decide that you want to try, taste everything, and then decide what you'll eat as your meal, then unless you are superhuman, you will probably not be able to do anything useful at that buffet, right? By the time you have tasted everything, you're already full. Then you have concluded that dosa was the best thing that was available there, but you no longer have room in your stomach for that dosa. Okay. Similarly, if you look at astronomy and astrophysics, if you look at the broad subgroups within that, you could start from something like um, studying the local stellar systems, stellar structure, evolution, interstellar medium, Milky Way galaxy, galactic structure, galaxy evolution, transients, large scale structure, cosmology. Now, within each of these subfields, you can have each of these fields, you can have another dozen subfields. So let's say there are, or even if we stick to the top 10 list that I gave, right? 10 broad disciplines within astronomy. Suppose you want to spend a year exploring each of them, you are going to be 10 years older before you even know what you want to work in. Okay. In those 10 years, the first thing that you had worked on will have evolved drastically. So now you have to go and study it again. So this mathematical optimization is actually mathematically impossible. Okay. So just like you would at a buffet, you try a few things, sure. But after that, once you have found something that tastes yummy enough, you just stick to it and eat it. You will be happier at the end, right? If you went to dosa counter at number 3, liked that dosa and started eating it, there's a small chance that counter number 9 might have had a biryani which you would have enjoyed more. But the amount of effort and time it takes to find that biryani is not worth the difference. Okay, so if I tell you that you have to eat either this or this, you tend to spend a lot of time agonizing over which of these two do I like better. But if I simply offered you a choice between these two dishes, both of which you like, instead of offering that choice, I said, do you want dish A? You would eat A and you would be happy with it. So when you're trying to select a field in astronomy that you want to work in, select a field that you enjoy enough. That's it. You don't need to find the best possible field to work in. Also, after your PhD, you'll continue in that area for a few years, but after that, you have the choice to change. So, for my PhD, I was doing my PhD at Caltech, which was the top place to study transients and the top place to do gravitational wave astronomy. And I didn't do transients or gravitational wave astronomy while I was at Caltech. I do both after I left Caltech, by the way. Right. So, what I do after my PhD has very little overlap with what I did during my PhD in terms of observing and data analysis and things like that. So it's not the final choice you are going to make. So you can choose things which sound interesting enough and then start working on them. That's the attitude you should go forward with.
Sir, for an example, I'll take one question over here.
Sure.
Worked on GRBs during my master's thesis.
That is the one that I answered already, Neha's question. Yes.
Yeah. So in this kind of question, I think just now what you answered, I think that applies to all such kind of students.
Yes.
And I think that is again up to the student to first decide in which branch he would like to work and whether it is
Correct.
comfortable for him, and then only he should go. So I think
What I'm saying is actually one step beyond that. What I'm saying is that as an undergrad, you have had very limited exposure to different subfields of astronomy, and don't use that to decide what you'll do for the rest of your life. Stay open. There might be other areas that you have not yet been introduced to, and those areas then might turn out to be great choices for you going forward. So just because you worked on something so far doesn't mean that's what you have to do for the rest of your life. One very particular thing I want to point out here is theory. Okay. There are two reasons why we have a lot of students who want to do theory. Okay. First is that uh, culturally we are obsessed with theory, right? Even back in mythology, there is value for something called pure knowledge, where you just sat on a mountain, thought about something, and you got pure knowledge. Um, the world is based on, or physics, astrophysics, even chemistry and everything are all called physical sciences. They are based on interacting with the physical world. Getting data through experiments, through observations, and working on them is extremely important. Okay. Second thing is that a lot of students don't get an opportunity to do experimental or observational sciences during their undergraduate because that requires a lot of resources which all places might not have. So that again means that students have only had a taste of theory and are saying that I want to do theory from here on. So imagine, for example, you grew up eating only Limlet toffees and you had never tasted a chocolate in your life. And you walked into a big sweet shop and said that, oh, there seem to be something called chocolates here, but I don't want that. मुझे lemon का गोली ही खाना है life भर. Some of you might like that consciously, but a lot of you might actually like chocolates better if you ate them. And if you are not open to trying out something that you haven't done so far, then you are not going to be happy. So keep that in mind. Don't remain obsessed with black holes being cool just because they were on Discovery Channel. Okay, just as you don't take inspiration from Karan Johar for deciding how you live life in college.
So there is one question based on what you just now mentioned. Maybe the student doesn't have people with whom he can work in his own college, so he has asked this question. I am a BSc student starting second semester this month. I would like to do projects on quite a few topics to see and decide my field of interest. How do I go about this?
Correct. So that is again what I answered in the buffet example, that yes, there are a lot of interesting looking counters at the buffet. You can't possibly eat everything, right? But the final thing you are trying to do is you are trying to find a career that you like. So what you are trying to be is happy. So instead of wasting a lot of time and energy on trying out everything, which will and figuring out which of them will make you marginally happier, once you find something that is interesting enough, go forward with it. Now, how do you find something that is interesting enough? Well, you start by reading material about it online from legitimate sources. One source which I had not mentioned so far is something called Astrobyte. So again, someone is asking, multiple students are sending me direct messages saying, can you name the books again? Can you name the sites again? Go to my website. I'm putting this here, star-iitb.in. This is our group's website, and all the resources that I'm talking about, most of them have been shared there. Okay. One great place to sample astrophysics research is actually reading research papers, but now that is actually very difficult. Sorry, I got distracted. Someone said PhD takes 28 to 30 years. No, PhD takes 4 to 5 years. You are 30 by the time you are done with your PhD. PhD doesn't take 30 years. Okay, coming back to the topic. Um, where was I? Yes. So in terms of resources, there's this blog called Astrobytes, because it's very difficult for an undergraduate student to read a paper. There are something like 70, 80 new research papers published every single day just in astrophysics. So even at my career stage, it is impossible for me to stay on top of it. So a group of PhD students around the world runs this blog called Astrobytes, where they take a research paper and explain it at a level accessible by undergrads. They'll also give you context of the field, which a research paper assumes. So for example, if I am publishing a paper on GRBs, I don't start by, oh, here is what a GRB means. So there are these things called stars, they explode, right? I assume that the readers are also expert. Astrobytes doesn't do that. They'll start by giving you a small explanation of what that field is, and then they'll explain that paper. So browse through Astrobytes to see what is the current latest research happening around the world, see what sounds interesting. You can't possibly do projects in all. Do a project in one thing. Then when you're how to do a project, I answered that INSA fellowship program, it's called SRPF, Summer Research Fellowship Program. So SRPF is a very good thing that you can actually apply for, get an opportunity. Maybe you will do a project on Nove, maybe you will do a project on cosmology, whatever it is. That just gives you experience of what research is like. For example, before deciding where to go for your BSc, you didn't go to every college around the country, attend one semester, and then decide that this is the best college where I should study. Right? Similarly, you can't possibly try every single thing before deciding this is the field I want to work in.
Uh, Sir, how a MSc specialized in electronics helps in astrophysics further? Furthermore, how to narrow down to a topic, because there are various interesting topics available in astrophysics and high energy physics.
Okay, so the second part I've already answered. I'm not going there again. Does a MSc in electronics help in astrophysics? It helps only if you are doing instrumentation, right? If you are working towards building telescopes of various sorts, ground-based, space-based, then your electronics background is helpful. Otherwise, not so much. Um, Engineering teaches you so electronics will have taught you a little bit of thinking from an engineer's perspective, and that can bring in a different angle to problem solving as compared to those with training in just pure physics, and that can be helpful at certain points. But if you want to use the electronic side of things, it matters only if you are specializing in instrument development.
Okay, I'll come to one question when the person has sent that question to me directly. AstroSat's multi-wavelength observation capability spans ultraviolet to X-rays, which involve vastly different photon energies and interaction mechanisms. How are the principles of electromagnetic radiation and quantum efficiency applied to optimize detector performance across this range, and how is cross calibration between instruments achieved to ensure consistent data interpretation?
Oh, that's a good question, quite a complicated one. So yes, the same detector can't work at all energies. right? So what we did in Astrosat is we decided these are the energy ranges that we want to work in. Well, I joined the Astrosat team rather late, so these decisions were done well before my time. In fact, they were done when I was still a high school student or a college student. Okay, so people said, okay, we want a hard X-ray telescope, soft X-ray telescope, we want a X-ray timing instrument, we want a UV telescope. And then with that, in each of those subfields, a lot of research has been done in saying, how do I detect hard X-rays? So we can use gas-based detectors, we can use scintillators, we can use solid-state detectors. And then for Astrosat, they said, solid-state detector is a new technology. We should actually try it in India. So they decided solid-state. In solid-state, then there are certain material characteristics that will allow you to decide. You need something that has a high band gap but is stable at room temperature. You want it to be high atomic number to increase the X-ray cross section. You want it to be electronically amenable to bonding with a ASIC. And based on that, cadmium zinc telluride detectors have been detected. So Astrosat team didn't decide, have been selected. So Astrosat team didn't say that given a universe that started with hydrogen, let me now find the optimal path to build a hard X-ray detector. No, hard X-ray astronomy is a large field. Hard X-ray studies the same detectors that we used in Astrosat and we'll be using on Daksha. So on each of these faces, you are seeing a lot of these squares. This is, I think, a 1/5 or 1/10 scale model. Each of these faces is actually a detector of this size and they are manufactured for using in advanced X-ray machines in hospitals. It's the same range of X-rays. So we build on top of all of that research, and that is true for all of research. So when finding what is the best telescope to use, we build on top of knowledge from a lot of different fields, and then we decide here is what we should do. Cross calibration is quite difficult. It is done by a combination of doing calibrations on the ground, calibrations in space, observing the same source with multiple instruments, observing jointly with other instruments. So there's a group called IACHEC, which is a collaboration of all the X-ray and gamma ray telescopes out there, and they together observe targets simultaneously to do cross calibration. So there is a lot of effort that has to go in there as well.
This question I'll take. Is it possible to work in space materials if I have done my MS in nanotech?
Yes.
There is one girl who is asking question again. She's a 9th standard student. She says, I'm class 9 student. So, sir, what kind of projects can I do now? And I'm really interested. And sir, I want to start from now.
I would say start with Apod. Okay, don't do projects in 9th standard. Okay, do reading in 9th standard. Don't try to overstretch too much beyond your grade. That is because you will just end up getting a headache instead of actually learning. Right. So astronomy picture of the day, I've just sent a link here. Every day they show a new picture. So at the very least, you get to see one pretty picture every day. Then on top of that, below the picture, they have given an explanation, and that explanation links to a lot of further websites with more details. So use that to explore astronomy and astrophysics. Go join your local astronomy club. Go for stargazing sessions. It will do two things. It will help you nurture your interest in astronomy, but it will also put you in touch with like-minded people who are at different career stages. Talk to them. They'll probably be organizing lectures. That way you'll get to learn more. Most of the large Indian projects and institutes hold a large number of outreach lectures online. For example, 2 or 3 days from now, TIFR is holding a lecture on YouTube by Subir Sarkar, who's a famous cosmologist from Oxford. And it will be broadcasted live on YouTube. So start attending things like that. Now in 9th standard, you might not understand that lecture, but there will be lectures at outreach level which you'll understand. So first get a feel of the field. Start seeing what you find interesting. This sounds good. Okay, go forward and do that. Right. And then as you go to 11th, 12th standard, make sure that you are understanding your basic physics and mathematics extremely well. And if you realize that you like stargazing but are absolutely hating mathematics, then that is a sign for you. For example, I can do enough mathematics to do my work, but I don't have a great aptitude for very complex math. So I don't do theory. And now some of you might say, oh, ये क्या है? ये तो astronomer है, math नहीं आता बोलता है. Yeah, and I'm still successful in my career, right? Everyone can't do everything. So you have to find out what works best for you. I'm very good at data analysis. I'm good at building instruments. I'm not great at doing complex 4-page long derivations which would be needed for quantizing gravity. So I don't try to work on that. Right. So find what interests you, what works for you, what you have the aptitude for. Work on honing those skills slowly. So in at school level, get a feel for astrophysics and then start doing well in your basic physics and mathematics, and then over time you start specializing. That would be the right way to go.
Sir, I think you have already answered most of these
So
questions.
so as an ending remark, I would like to say one more thing. Okay, I'm just scrolling at some of these questions as they are coming along. Um, some of you are asking highly personalized variations of the same question, and that's not a great place to start. Okay. If you have done so and so topic at so and so place, and now you want to apply to so and so thing, it's your journey. You should figure it out. Right. Don't get someone else to write your SOP. Don't expect that the universe will have created a tailor-made scholarship just for you. Okay. One question which came a couple of times is if you are wanting to go for a PhD, make sure you get some kind of a scholarship. Fellowship are larger than usual scholarships, but whenever you are doing a PhD, you'll usually get a stipend. You don't have to pay anything out of pocket. The stipend all across the country is enough to actually sustain you. It will take care of your needs. You will not save a lot of money for other things, but usually it is enough. Similarly, around most of the places in the world, you'll get enough stipend that you can live by. But finally, this is your journey and you have to do it. So if you are trying to ask me for a project here, that's cheating. That's not what this session is about, right? Or if you are trying to ask me for personalized recommendations, again, that's not what this is about. As professors, our job is to show you the way. You have to walk the way. It's your career. It is your responsibility. If you follow the path that I suggested today, for example, and then come back to me crying 10 years later saying, oh, मैंने ये try किया, it didn't work for me. I said, I'll say, oops, sorry. But I'm not going to rewind time and push you on another path, right? I can give suggestions which sound correct to me. Actions आपको करने हैं, decisions आपको लेने हैं. It's your career. So make sure that you are actually taking ownership of that. Okay. So I think we should probably close on the questions here. So thank you everyone. Go to my website. You'll find more details there. There's also a large number of my talks that are available on YouTube. So if you want to look at any of those things, then go and look those up as well. And the same holds true for a lot of the leading astronomers around the country. Thank you.
Sir. Thanks a lot. Your lecture was very interesting in the lucid manner that you have explained everything. It's really wonderful. And especially towards the second part of the session, you have given clear idea to the students about how to decide the field of their choice, of their interest, how to actually then prepare themselves to work in that field, and how to apply, how to actually do the previous research in terms of which institutes they can work on the topic of their choice and so on. It's really very well explained, and I'm sure now students will take their decisions on their own by doing some background research work on how to select a topic and which institute they should go for, and they will now hereafter write very nice SOPs. Thank you very much, sir.
Welcome. My pleasure. Thank you all. Bye.
Thank you, Varun sir. I just want to I just want to say that Varun sir was very much instrumental. No, the first person I approached when I wanted to plan this winter school. So he was very much, no, instrumental in deciding the structure for this. Thank you very much.
You're welcome. Thank you.